Okay, hello. I don't usually title my videos. I never know exactly how far I'm going to get before I hit stop record. Um, but for this one, I came up with a useful title: GCF versus LCM versus CIA versus FBI versus GOP versus. I, I could spend the rest of the video just listing not just abbreviated names for things, but three-letter abbreviations of things, right? Just recognizing that this is a three-letter name for something doesn't really tell you what it is. The grand old party has nothing to do with the greatest common factor, right? They both start with G, completely separate things. This is the Republican Party in America. It didn't start being called the GOP when Lincoln and others kind of formed the party back in the 1850s. But at some point, this isn't a history video, so I'm not going to get into the history, but at some point it got the nickname of the Grand Old Party. And so now you see GOP listed more often than R when talking about Republicans, right? Central Intelligence Agency has a lot in common with the Federal Bureau of Investigations, but even these two I's aren't the same. No, I put serifs on that I, not this one, right? Those intelligence and investigation, two different words, both using the I, right? But because we know what these are, we don't usually get those mixed up. In math, people get the GCF and LCM mixed up all the time. And it's because they don't actually know what those words are that are being used. They just know you learn them around the same time in your arithmetic or algebra class, whether that's junior high or high school or college. These are often taught near each other, and we don't have a lot of three-letter abbreviations in math, so we're getting it mixed up. But GCF, let's think about what each of those letters mean. GCF is greatest common factor. LCM is least. C is the same as C, least common multiple. So if you watch my last video, you heard me stress the definitions of factor and multiple are so important, because if we get factor and multiple mixed up, then it's really easy to get these two things mixed up. So let's review. A factor in this context, we're starting with particular numbers. So let's give ourselves an example here. GCF and LCM of, let's say 10 and 35. Okay. All right. So if I'm looking at the greatest common factor, I'm looking at the factors of 10 and the factors of 35. If I'm talking about LCM, I'm looking at the multiples of 10 and multiples of 35. So what are these things called factors? Let's make sure I type the same definition this time that I gave last time. Factor is a whole number that can be multiplied by another whole number to result in a given number. When I say goes into, we're saying we can do the long division and get a quotient that comes out cleanly, right? You can get a whole number. When you're doing 10 divided by 2, the quotient is a whole number, right? 2 goes into 10 evenly. That means I can do 2 times some other whole number to get 10. Okay? So 10 divided by 2 is 5. That's how I get that other number. So that gets me 10. So both 2 and 5 are factors of 10. 5 is a factor because 5 times something gets me 10. Well, I already have it written here. 5 times 2 is 10. What are the other factors of 10? Well, 2 and 5 are both prime. So the only remaining choice is 1 times 10 or 10 times 1. There's no need to keep on listing them both, right? So I've got 2 and 5 and 1 and 10. If I list all the factors of 10, I got my list here, 1, 2, 5, and 10. And I can do the same thing for 35. So 35, well, I've always got 1 and 35. Right? You can always do 1 and the actual number. But then it's a question of, well, what else goes in there in between? Well, 35 ends in a 5. So I know it's going to be 5 times something. We talked about those divisibility rules recently. Okay. Well, I can do the long division. 35 divided by 5 is 7. And so 5 times 7 is 35. And 5 and 7 are both primes. So again, I have exactly 4 factors. So it's just coincidence that for each of these numbers, I have 4 factors of 10 and 4 factors of 35. So that's factor. Now, a common factor, to be in common means you share it with something else, right? So we don't usually bother with giving this as a formal definition, but I think it can be useful to actually say a common factor is a number that is a factor of multiple given numbers, right? Most often when we're talking about GCF and LCM, we're looking at 2 particular numbers, but I could expand this. I can look for the GCF of 10 and 35 and 14, or the LCM of 10, 35, and 14, right? So what is a factor that all 3 of these have in common? Or what is a multiple that all 3 of these have in common, right? But we don't want to get ahead of ourselves. Have to walk before we can run, right? So a common factor is a number that is a factor of multiple given numbers. So is 1 a factor of 10 and a factor of 35? Yes, 1 is here, 1 is there. Yes, so 1 is a common factor of 10 and 35. Is 2 a factor of both of these? Well, 2 is a factor of 10, but it's not a factor of 35, right? Is 3, I don't have to worry about 3 or 4 because they're not in my lists here, right? I'm only looking at these 8, including some redundancies. So the next number here is 5. Is 5 a factor of both of these? Yes. So let's circle that. So common factors, I've got 1 and 5. Is 10 a common factor? Well, 10's on this list, not over here. Okay, and that's this half exhausted. Now I look over here. I've already got 1 and 5 listed. 7's a factor here. Is 7 in this list? No. 35 is a factor here. Is 35 in this list? No. So for 10 and 35, they have exactly 2 common factors, right? To be a common factor, it has to be a factor of 1 and the other number. Not the number 1, but the first number, and has to be a factor of the second number and third and fourth, however many given numbers you have. Well, greatest just means you look at this list of common factors and say, which one's the greatest, right? It's a finite list. If we keep on going, whichever number is the biggest one here is the biggest in that list. Well, our list only has those 2. I don't want to confuse you with indicating that it has more. So greatest common factor is very simply the greatest I'll just change the word a little bit in case you forget what greater means. Right? The greatest, the largest, the biggest, those all mean the same thing. The largest number that is a common factor of multiple given numbers, right? So it's the same definition as common factor, just the greatest of those. So between 1 and 5, which one's bigger? 5 is bigger. So the GCF here is 5. I'd say the GCF of 10 and 35 is 5. Okay. Now, if I switch over to multiple, instead of the definition of factor, I need the definition of multiple, right? That's similar to factor, but different enough. We'll start from scratch here. Multiple is a number that can be achieved multiplying given numbers. Oh, sorry, by multiplying a given number by some other whole number, right? So in green here, I've got all the factors of 10 and all the factors of 35. How did I get that? I started with 10 and looked for smaller numbers I could multiply to get 10. Well, for multiple, I'm going in the exact opposite direction. I'm going to start with 10 multiply by some other whole number. So I'll start with the smallest one I can think of, the smallest one that exists, and that's 1. Right? If you do 10 times 0, you get 0. 0 doesn't really count as a multiple. Right? This is one of those times where definition of whole number, we're excluding 1. Sorry, we're excluding 0 from being a whole number. We'll call that a natural number. All right. So the next smallest whole number after 1 is 2, and the next smallest is 3 and 4. So 10 times 2 is 20, 10 times 3 is 30, 10 times 4 is 40. And it might take me a while to get all of these. In fact, it will take an eternity, right? I could do 10 times 8 billion and 7. Well, that'd be 80 billion and 70. I'm just shifting everything over one place. But there is no greatest multiple. The smallest multiple is the number itself, and then we're getting bigger and bigger and bigger. Just like the least factor is always going to be 1. In every list of common factors, you're always going to have 1. It's not interesting to talk about the smallest common factor. 1's always going to be your answer. Right? We want the greatest number on these limited lists. This list has a ceiling of 10. This list has a ceiling of 35. So we're looking, how big can we go and still be under that ceiling, right? Still be one of those factors. LCM is the opposite. The smallest multiple of 10 is 10. So the least multiple of 10 is obvious. The least multiple of 35, if I start writing these out here, so 35 times 1 is 35. 35 times 2 is 70. 35 times 3 is 105. 35 times 4, well, 30 times 4, that's 120. 5 times 4 is 20. 120 plus 20 is 140. And I could keep on going here. How do I know when to stop? Right, listing these multiples of 35, I could go on for a long time. Listing these multiples of 10, I could go on for a long time. How do I know when I've reached a common multiple? Well, I just have to look at those lists, and until I see one that they have in common, I have to keep on going. Now, because I used a nice number like 10, I hope you all recognize that 70 and 140, right? Any number that's ending in a 0 is a multiple of 10. So if I'm looking for common multiples, I've already got 70 and 140. Oh, I should give our definitions here first, right? So common factor, I have common multiple is a number that is a multiple of multiple given numbers, right? So here's where the English language gets kind of annoying. Multiple given numbers just means more than one, right? Here I'm using multiple in two definitions of the word. Multiple of a given number, that number times another whole number. A multiple of multiple given numbers, right? That's just how English works. So the multiple of all of these given numbers, that's what it means to be in common. So far I have two examples of a common multiple. The greatest, I'm going to keep on going. 70 is a common multiple, 140 is a common multiple, 210, that's 35 times 6 and 10 times 21, right? This list of common multiples has no ceiling. It's going to keep on getting bigger and bigger because both of these blue lists of multiples are getting bigger and bigger, right? So we never want the greatest common multiple. That would always be not technically infinity, but there is no greatest. We want the least common multiple. We want the smallest number that is a common multiple of multiple given numbers. So maybe having this multiple is not so nice. Let's say the smallest number is a common multiple of each or of every given number. Common multiple is a number that's a multiple of every given number. Maybe that language is a little bit nice, so I'll make a note of that. All right, so common multiple is a number that is a multiple of every given number. The least common multiple is the smallest number that is a common multiple of every given number. So I've got a list of 2 here. That's enough because even though this list is going to grow forever, I'm already at its floor, right? The only possible number lower than 70 that's a multiple of 35 is 35. And 35 is not a multiple of 10, right? I jumped from 30 to 40. So out of this list, if I put my dots, right, it does keep on going. 70 is the least of those. So the LCM of 10 and 35 is 70. Okay. Now that is a strategy that works for really nice and really small numbers. But listing out these multiples and listing out these factors is not a very nice strategy when we want to find the GCF and LCM of 520 and 528. Listing out all of the factors here, it's going to take a long time. Listing out all of the multiples, first, getting any multiples of 528 is a pain, right? Doubling 5, doubling 28, I guess that's 1,056. Double that, 2,112. I'm not going to be able to keep track, right? 528 times 3, that I'm not doing in my head, right? There's a lot of computation just to get the first 3 multiples of 528, let alone get a high enough number on that list so it's also showing up on this list, right? This strategy of listing multiples is only very occasionally useful. Unfortunately, most of the examples that you've been using are pretty small numbers, and so you get used to that strategy working. But once you get past kind of the grade school level usage of this, we need a better strategy. And that strategy uses the prime factorization. Why do we care so much about this prime factorization of 528 and this prime factorization of 520? Because that's going to guide us straight to both the GCF and the LCM. So let's write this down. So this was from an earlier video, 520. We can split that up into the factor pair 52 and 10. Keep on going to all possible factor pairs of those earlier branches until we get to prime numbers. Here we hit the prime numbers earlier, so we just brought those down. So I had 3 2s, a 5, and a 13. So I'm going to write that down here. 520 is 3 2s, and I'll write them out for a reason you'll see in a little while, and a 5 and a 13. Versus 528, let's space that over a little bit here. Just center it. There you go. So 528, we saw that was 4 2s, a 3, and an 11. So we've got 4 2s here. I saw 11. What was the other one? A 3 and an 11, right? Because we had 66. Okay. Now, we said all of the factors of 520 are composed of these building blocks. All of the factors of 528 are composed of these building blocks. So any factor that's a factor of 520 and that's a factor of 528 will be using building blocks that are on both lists. So let's think of 13. 13 is a factor of 520. Is 13 a factor of 528? No. So 13 is not a common factor. So any common factor of these will not have 13 as a factor of it because it's not on both lists. So we have to identify what number shows up in both lists. Well, here's a 2. And here's a 2. So 2 is a common factor of 520 and 528. But here's a second 2. And here's a second 2. Well, 2 times 2 is 4, right? 520 is 4 times 130, right? 2 times 5 is 10, 10 times 13 is 130. So I can say 520 is 4 times 130. 528 is 4 times all of this. 2 times 2 is 4, 4 times 3 is 12 times 11. We already saw that's 132, right? So 4 is a factor of this, 4 is a factor of that, 4 is bigger than 2, 4 is a common factor. But it's not the greatest because look, there's another 2, right? I don't need to do 4 and 130. I can keep going with the third 2. I can say this is 8 times 65. If you don't think 5 times 13 is 65, go do it on your own and tell me what it is instead, right? Or 8 times 2 times 3 is 6 times 11, 66, right? Now 65 and 66 are pretty close, but they're not the same number. Now, this should actually make a lot of sense to us. This is saying if I add up 65 eighths, I get to 520. This is saying if I add one more 8, if I go from 65 eighths to 66 eighths, I get 528. Well, of course, that's 8 more than 520, right? This is 65 eighths, 1 more, 528, 66 eighths. Right? So the numbers are close together. So this second factor of counting eighths is going to be 1 away because they're 8 apart. Okay? And this is also showing me 5 is here, no 5's here. 13 is here, no 13's here. I have a fourth 2, but I don't have a fourth 2 over here. I only had 3 2s. So I can't list that extra 2. I don't have 16 times 33, right? If I split it here, 2 times 2 times 2 is 8 times 2 is 16 times 33. And then 16 times something over here. 16 doesn't work because I don't have another 2 to multiply the 8 by, right? And then 3 and 11 are not on this list. They're only over here. So my GCF is 2 times 2 times 2, which is 8. Now, for finding greatest common factor, one great advantage of this method is the LCM is staring us straight in the face as soon as I explain how to do that, right? When you are adding fractions and you're talking about common denominator, which is just the LCM of the denominators, or you're trying to reduce and you're looking for common factors of your numerator and denominator, it's very common that people can find a GCF or find an LCM without all of this information. And then what they're actually trying to do is stymied beyond that, right? Just finding the LCM is rarely what we want to do. We're finding it for a particular purpose. Same thing with GCF, right? We want to do something with that GCF. Well, but let's see where we can go from here, right? When I say that 520 is 8 times 65, and 528 is 8 times 66, seeing these other numbers here is the key to both the LCM and to the other things we use factoring for. The LCM is going to be my 2 times 2 times 2 times the remaining numbers here times my remaining numbers here. That's times 2, not 12. Times 2 and 3 and 11. The 5 times 13, I've already calculated, that's 65. The 6 times 11, I've already calculated, that's 66. The 3 2s I've already calculated, that's 8, right? To find the LCM, I'll just write this as a sentence. LCM, 2 numbers, is always equal to the product of their GCF I've never found a better name for the rest of this, right? So let's just put that in quote marks, because this is not going to be in any textbook or math dictionary, right? The leftovers, decent mini series from HBO. Also, what I'm calling this 5 and 13 and 2 and 3 and 11. These remaining factors from our original numbers are super important, both for the LCM and for factoring and fractions and all sorts of good stuff. But for right now, for the LCM, we're going to take the GCF, in this case, 8. I don't know why I wrote over that, right? The 8 times the remaining factors here and the remaining factors there. So 8 times 65 times 66. So if I do that by hand, do 65 times 66. 6 times 5 is 30. 6 times 6 is 36. Okay. Well, if 6 times 65 was 390, then 6 times 65 is going to be 390. So 0, 9, 9, 10, 11, 12. 3 plus 1 is 4. 4,290. So let's think about this. Is 4,290? Oh, I forgot about the 8. So take that 4,290 times 8. 8 times 0 is 0. 8 times 9 is 72. Times 2 is 16. 3. Times 4 is 32. 33, 34. Okay, 34,320. I'm claiming that is the LCM. It's a 4, not a 9. 34,320. Well, how did I calculate that? I did 8 times 65, which is 520. 8 times 65 times another 66. Is that a multiple of 520? Of course. It's 520 times another whole number. Well, how else could I think about getting 34,320? I did 8 times 65 times 66. Well, the associative property says I can do 8 times 66. 8 times 66, that's 528. And then multiply by 65. So is this number a multiple of 528? Yeah, it's 528 times another whole number. Okay. So 34,320 is a common multiple of both 520 and 528. And because 65 and 66 have no factors in common, fancy name for that is relatively prime. Let me just sneak one more definition in here for us. Relatively prime means no common factors besides one, right? So relatively prime, that's an adjective, right? A number that's prime means it has no factors besides one and itself, right? It has exactly 2 factors, one and itself. So if we're using prime as an adjective, 3 is prime because its only factors are 1 and itself. Well, 65 is not a prime number. 65 is not a prime number. It has factors, 5 and 13. 66 is not a prime number. It has factors, 2 and 3 and 11 and 6 and 22 and 66. Whole bunch of factors. But none of its factors are also factors of 65. They have no common factors. So relative to each other, right, they're prime. They might as well be a prime number compared to the other one, right? No factors in common other than 1, because 1's a factor of everything. So there's one more bonus definition for you. To find the LCM, you always multiply the GCF times whatever prime factors are remaining here. And that will give you the least common multiple. There's no way you're going to get 34,320 using this strategy, right? I'm not going to sit here and list the first 66 factors of 520 without making a whole bunch of mistakes, right? And spending a few days just working on that one problem, right? So we really want this strategy. And as I've said several times, it's going to pay off in later situations as well. So there's our GCF, our LCM, and ways of getting them.